Okay, here we go with the start of relations and functions, and this is picture patterns. So if we take a look, we're going to look at some patterns in some pictures. The first three figures below show cubes made from toothpicks and marshmallows. So as a marshmallow, you stick toothpicks and you make a cube. In this investigation, we're going to examine the relationship, because we are doing relations and functions between the number of cubes and how many marshmallows it takes to make that number of cubes. So the first one is complete the picture for 4 cubes. So we're just going to have to kind of extend this out a bit. Like so. Put in some marshmallows to hold things together, and there is our 4th cube. So there is a relation between the number of marshmallows and the number of cubes. In this situation, the number of marshmallows is dependent on the number of cubes we are making. Therefore, we say the number of marshmallows is the dependent variable. And what it depends on, the number of cubes, is the independent, which in is the fancy way of saying not dependent variable, the independent variable. The relation between the number of marshmallows and the number of cubes can be represented as a table of values. In a table of values, the independent variable is always in the first column, independent, and the dependent variable is in the second column, dependent. We often use a single letter to represent the variable, so we're calling the number of cubes C and the number of marshmallows M. Use the diagrams above to complete the first 4 rows. So we're going to go up here, we're just going to count. I need 1, 2, 3, 4, 5, 6, 7, 8 marshmallows to make cube number 1. I've got the 9, 10, 11, 12 to make cube number 2. And it's something that you can count for yourself. So 16 and 20. And you'll notice that we can see a pattern here. If I increase the number of cubes, my number of marshmallows also increases by 4 each time. So, table of values, one way of getting a relation. Another way is as a set of ordered pairs. In a set of ordered pairs, the first element is the independent and the second is the dependent. Independent, dependent. An ordered pair is enclosed in parentheses and a set is enclosed in brackets, or sometimes these are called brace brackets. So if we want to finish off, we have 316, comma, and you put a comma in between the ordered pairs. 420.
Please come to the office, please.
524,
thank you.
628. So that is a set. This means a set, this notation. A set of ordered pairs. Second way of representing a relation. Domain is a set also, but of elements of the ordered pairs. The first element, 1, 2, 3, 4, 5, 6. Now, it doesn't matter what order they're in, but if we can, putting them in numerical order makes our job a little bit easier. It makes it easier to see all the elements and how many we have and all of that. The range is the set of all second elements. So that's how many marshmallows we have. 8, 12, 16, 20, 24, 28. Now you notice we lose some information just listing domain and range. Here we know that 1 goes with 8. Here we know that 1 is the first element and one of these guys will be the second element that goes with it. And we could assume, but we don't know for sure, that 1 doesn't go with 28 and that 6 doesn't go with 8. So we lose information listing the domain and range, which information we have in the set of ordered pairs or the table. Now, let's look at a couple more ways. The relation between the number of marshmallows and the number of cubes can also be represented by an arrow diagram. You write down the elements of the domain. And oh, by the way, when we do domain and range, we only list an element once. No matter how many times it may occur, the number is only ever listed once. And the same thing happens in an arrow diagram. Now in this particular case, everything only occurs once, so that makes it pretty easy. So this is the domain, which is the independent. This is the range, which is the dependent variable. And to finish this off, so this has the domain and range, just like domain and range, but it also contains the information as to how we are going to make an ordered pair. So here we know that 6 goes with 28, that 1 goes with 8, and so on. So from an arrow diagram, we could do the table, or the set of ordered pairs. Next up is a graph, and I believe that I have a recording that takes over at this place, so I'm going to join the two recordings together to make one glorious recording, and this will be the next way of looking at a relation. Okay, so we have table of values, a set of ordered pairs. Domain and range aren't a way of looking at a relation. They're a way of listing information about a relation, but we don't get the relation from it. Okay, so I'm going to leave this here, put the two together, and hopefully it all works out. Okay, so let's graph this. So what goes in this box? What do we put here? What's the label?
The number of marshmallows.
Number of marshmallows. Now what goes down in this box down here?
Number of cubes.
Number of cubes. What numbers do we have to put that aren't in the number of cubes? This scale goes by how much? Ones. What goes now? What goes up here? Okay, is that good enough? Do I need to go any higher? No. Okay, so 1 goes with 8. 2 goes with 3 goes with 4 goes with 5 goes with 6 goes with 28. This is another way of showing the relation, right? We can represent it as a graph. Dependent variable is always on the vertical. Independent is on the horizontal. The scale in any particular direction needs to be the same. You cannot change this and go 1, 2, 5, 9, whatever. And here it's by 4s. Always look at the scale, because a lot of times we just figure that it's 1s, and sometimes it isn't, and you can get into trouble looking at a scale and then figure out it's just by 1s, and it really isn't. So make sure you take a look. You probably noticed that all the points plotted lie on a line. Should you connect the points with a line? So should we join these? By connecting the points, this means that every point, including the ones between the points you plotted, makes sense for this situation. So note, if you do draw a line, it's going to go through 1 1/2, 10. It'll go through there. Which means that you can make 1 1/2 cubes with 10 marshmallows. Does that make sense?
No.
No. Should the points be connected?
No.
No. So anytime we draw a graph, that's something we have to ask ourselves. Does it make sense for us to connect the points? Okay, or not? If it makes sense for the points to be connected, then we say the data is continuous. If it does not make sense for the points to be connected, then we say the data is discrete. Okay? So we have discrete and we have continuous graphs. In this situation, the data is discrete. I'm just going to go to page width here. There's a dash in there. What makes sense to put in there? kind of. It's like, we could say it's not continuous, but that doesn't fit in here. I don't know. So let's just say it's discrete data. I'm sure there's something somebody was looking for or had in mind when they wrote this, but I don't know what it is. And therefore the points, circle 1, should or should not be connected. Should not. And circle 1, I'm also going to cross 1 out, right? So we say, if it's discrete data, then it only makes sense to have whole numbers of cubes, right? You can have 1 cube, 2 cube, 3, and so on. And therefore you only have whole numbers of marshmallows. If you examine the values in the second column of the table of values, you may have noticed that the pattern in the second column of the table of values is to add 4 to the previous number, right? So when we were back here and we were filling in the table and we'd done this by counting, right? 1 and we counted 8 and we counted 12. We looked at the pattern and said, hey, you're just adding 4. So probably the pattern continues that way, just to add 4. So you get to the number on the, so what if you wanted to determine how many marshmallows are needed to make 56 cubes? Would you keep the pattern going until you hit 56? No. One way to determine the answer is to keep adding 4 to get to the 56th row, but you just said, I don't want to do that. Instead, it may be better to find a rule that relates the number of marshmallows to the number of cubes. Examine each row of the table to find a rule that relates the number of marshmallows to the number of cubes. So you want your rule to say something like, take the number of cubes and do this, and you will get the number of marshmallows. Okay? And that will be our rule. Check to see the rule works for other rows in the table, and then write the rule by completing the following statement. So we're going to write this in words. So how do we represent a relation? We started with a table of values. We have a set of ordered pairs. Domain and range do not represent a relation. They give us information about it, but we know that just given the domain and the range, we cannot build the relation. So we've got table of values, set of ordered pairs, an arrow diagram, and a graph, and now we've got words. So, does anybody have a rule in words that will relate these?
Multiply by 4, add 4.
Multiply by 4, then add 4. Okay, so I want to actually check that out. So I'm going to go back to the table. 1 times 4 is 4, plus 4 is 8. 2 times 4 is 8, plus 4 is 12. 3 times 4 is 12, plus 4 is 16. 6 times 4 is... So that seems to work, right? I can generate any of these numbers here from the number of cubes. Okay, so I think we have a good rule. The relation between the number of marshmallows and number of cubes can also be represented as an equation. So how many ways do we have now? We have a table of values, a set of ordered pairs, an arrow diagram, a graph, words, and now an equation. So there's 6 ways that a relation can be represented. Use your algebra skills to translate the rule above from English to the language of math by completing the following equation, using M to represent the number of marshmallows and C to represent the number of cubes. We get M equals 4C plus 4. Okay, and all we've done there is, it looks like 4CT4 or something like that. Right? So 4C plus, so that's why I draw T's like this. Okay, that's why I do X's like this, so that we don't confuse a plus or a multiply. Right? So you may want to do that. Math. Use your equation to determine the number of marshmallows that are required to make 56 cubes. So what do we do? So I have an equation. Equation is like a formula, right? So remember the secret to math. Formula, substitution, answer. What do I substitute and where do I put it? Okay, so I make C 56. It's my substitution. So what is that? 224 plus 4. So what's M equal to? 228. So if I say I want to make 56 cubes, then you can say, well, you're going to need 228 marshmallows. Right. So, you know, if you're sending your mom to the store to buy the stuff, you're going to say, get a bag of at least 228 marshmallows so that, you know, I can make these 56 cubes. Your equation can also be used to determine the number of cubes if you know the number of marshmallows. Use your equation to determine the number of cubes that can be made with 460 marshmallows. First step, do what? What'd you say? Write down the formula, because Mr. Henry has been telling us that all along. Is the first step is always to write down the formula. Okay? Whatever formula you're using. By writing down the formula, you're communicating, right? You're telling me or anybody else looking at it. If you've got a friend that says, show me the answer to this one there. If they look and they see the formula, they at least know, okay, we're starting with that formula. They could ask you, why are you using that formula? Or whatever, right? If we don't write down formulas, then we're just starting with a bunch of numbers written down. And what does that mean? You know, then it's legit to ask, where did that come from? What does it mean? You just wrote like 4 times 56 plus 4. You can't just randomly write 4 times 56 plus 4. It makes no sense. But if you write m equals 4c plus 4, and then you write m equals 4 times 56 plus 4, if you know what m and c are, it starts to make sense. Okay, what goes in for what? So 460, what are we solving for? C. What's our first step in solving? What should you do? Subtract 4 from where? Both sides. Okay, I don't need to write little minus 4s here, right? Because I know what we're doing. We can do big kid math. Right? If you need to write it down, go ahead. I'm not going to, say anything about it. But, we know. How did you get from here to here? Most people are going to go, looks like you subtracted 4 from both sides. Why'd you do that? Well, 4 was out. We need to get rid of this 4. We do that by subtracting. Okay, what's the next step? Divide both sides by 4. While I'm doing that, I'm also going to flip the sides, right? Because I want my variable on the left so that it says C equals. Okay, so it says C equals 1, 1, 4. Right? You just do 456 divided by 4. And so how many cubes? Okay, so you could write we can make 114 cubes with 460 marshmallows. What if it came out to, what if it was 462 marshmallows? We got like 114 and a half. What would you say? You would say 114, right? You'd say, well, I can't do a half a cube, so I would eat 2 of the marshmallows and then make 114 cubes. Right? And here we could say we need 228 marshmallows to make 56 cubes. That puts context into it, right? I mean, if somebody's looking and sees the m, like if all you see is what's written here, m equals 4c plus 4, and it's 4 times 56, da-da-da-da, this sentence saying we need 228 marshmallows to make 56 cubes makes it kind of obvious. Well, m is 228, so that's the number of marshmallows. C is 56, because I can see a C here, and now it became a 56. So C was replaced by 56, therefore C must be the number of cubes, right? So there's stuff that we can get out of this, right, by looking at it with the formula. Okay? Same thing here. Ignore everything but what's written. Okay, so you look at this. And remember, you don't know marshmallows are cubes, right? All you know is m equals 4c plus 4. 460 equals blah, blah, blah. Solve for c. It says we can make 114 cubes, so c must be the number of cubes with 460 marshmallows. Okay, so somebody's doing weird stuff with marshmallows and cubes, but that's what it means. Let's look at the relation between the number of toothpicks and the number of cubes. Use the diagram in your patterning skills once again to represent the relation as a table of values. Okay, so if you flip the page over, which is what I think you have to do probably, then 1 cube takes how many toothpicks? 12. Okay, so you went back, counted up. 2 cubes takes how many toothpicks? 3 cubes takes how many toothpicks? 4 cubes takes how, what are we going to do to get the rest of them?
Add 8.
Okay, are you going to count? I'm not counting the 44 in that, right? I'm just saying, well, looks like you add 8, right? So we have a table of values. From that, we can represent the relation as a set of ordered pairs, right? Okay, what do? So you put down a brace bracket which says what follows now is a set. You list the ordered pairs, so 1, 12, 2, 20, 3. So make sure that the ordered pairs are within parentheses and that there's a comma between each set of parentheses. So 328, 436, 544, 652. And I'm done, so I'm going to close off. Right? Question? Nope. So far, so good. State the domain and range of the relation. Domain is a set of numbers, and therefore you need that brace bracket, right? D, that stands for domain, equals the set. And what are the numbers in the domain? What kind of variable is that called? The independent variable, right? So the domain is the independent. We often call it the x's, right? Because when we talk about, usually we talk about x's and y's when we're graphing. Here we're not. We're talking about m's and c's, right? Or c's and m's. But usually it's x and y. What's the range? Well, the range is the set of the second elements of the ordered pairs. And how many do I have? 1, 2, 3, 4, 5. One more. They don't have to be written in order, but it's better if you do. Represent the relation as an arrow diagram. So far, information is maintained here, right? Table of values, we know what 1 and 12 mean. Ordered pairs, we know what 1 and 12 mean. We know they go together, right? 1 goes with 12, 2 goes with 20, and so on. Domain and range, we now lose that information. We know what is allowable as the independent variable. We know what is allowable as the dependent variable, but there's nothing here that says 1 goes with 12, 2 goes with 20, and so on, right? So domain and range, you're losing information. But an arrow diagram, you list the domain vertically in the first oval. You list the range vertically in the second oval. And now you make the connection. So you say 1 goes with 12. And this is just kind of a fairly basic, boring one, right? There's nothing exciting here. Everything goes, not like it's crossing over. But in essence, it takes the domain information, which is here, and it takes the range information, but it has more information than that, right? Contained within the arrow diagram is also how each element of the domain relates to an element of the range. So if I give you an arrow diagram, you can build a table of values. You can build a set of ordered pairs. Okay? You have all the information that's in the relation. Represent the relation as a graph by labeling the axes. So this is the number of cubes. 4, 5, 6. We went up to 6 cubes. What goes in here? The number of toothpicks. So we need labels, right, to give us the information. We got cubes and toothpicks. What goes on this one? Is 32 good enough, or do I have to keep going? Got to keep going, right? And I think 56 is high enough, right? So we now graph, so we go back and we can look at. So we can either look at the table, from the table say 1, cube, 12, 2, 20, and so on. We can look at the ordered pairs, 112. Remember, this is your x value and this is your y value. Or in this particular relation, this is your c value, number of cubes. This is your t value, number of toothpicks. Okay, so really what's being graphed is we could say this is the c-axis for cubes and this is the t-axis for toothpicks. And then we get our ordered pairs, right? So 112. 2, what did 2 go with? 20. Where's 20? 20. No, 2. Right. 3 goes with 28. 4 goes with 36. 5 goes with 44. 6 goes with 52. How are we doing? We all got the graph drawn? Anybody not? Yeah, I still. Okay, so I'm going to give you a moment to finish off the graph. We have a set of pairs in a straight line, and the question that always begs to be asked is, should we join the points and make a continuous line? So, yes or no? Is this data continuous? Can I have 1.732 cubes? Can I have 1.5 cubes? No. If it's not continuous, then it is discrete. Do we draw a line? No. Write a rule that relates the number of toothpicks to the number of cubes by completing the following statement. To determine the number of toothpicks needed, take the number of cubes and times by 8 and then add 4. So let's say and multiply by 8. That's the $1 word for times, which is a 10-cent word. Multiply by 8 and add 4. You got a rule. What should you do with your rule? Just like factoring, you should check it, right? Make sure it works. Okay, 1 times 8 is 8, plus 4 is 12. 3 times 8 is 24, plus 4 is 28. 6 times 8 is 48, plus 4 is 52. Okay, I'm convinced. So check your rule. You're going to do this a lot in math. You're going to come up with stuff. Hey, I looked at the pattern, and I think that's the rule, but I better make sure that it works for more than just one number. It's easy to find a rule for the first line, but if that rule doesn't work for the second line, then you need a new rule. Represent the relation as an equation using the variable t for toothpicks and c for cubes. And so what is the equation? Well, how about t equals? So this says the number of toothpicks needed. Take the number of cubes. It really should like be an is in there. Equals translates to is. Take the number of cubes and multiply by 8 and then add 4. Okay, so 8c plus 4. If I want to make 36 cubes, what do I do? What's the first step? Write your formula. Writing the formula gives the answer some context, right? So people know this is what I'm doing. I'm taking this formula. Okay, let's substitute in. What do I substitute 36 for? T or C? 8 times 36 is 288, right? 288? 280. Plus 4, so t is equal to? Okay, so to make 36 cubes, we need 292 toothpicks. Or we could say 292 toothpicks are needed to make 36 cubes, right? Just anything that along those lines. Use the equation to determine. What does determine mean? Show work. Will you see the word determine in the multiple choice or numerical response portion of your test in a couple of days? No, because you cannot determine. Right? All you can do is answer. Now you should determine everything, right? In other words, you should show all your work. And it's really important for Thursday's test, because when you get it back Tuesday, if you got something wrong, we want to be able to look at it and say, okay, see this? Yeah, your signs are reversed or something, right? So there needs to be something there. You need to know what mistake you made, because you only have a day to get that fixed, right? We got to fix it Tuesday after you get it back. We have a class. You got that night. You got Henry's after school and all that. But you want to get it fixed hopefully in class, right? Just sit down and say, okay, I see what I did. Show your work. Determine the number of cubes to be made with 1,964 toothpicks. So what do we do? First step. Formula. Thank you. Okay, what's the 1964? T. I remember 1964. I was alive then. Okay, what's our first step in solving? Subtract 4 from both sides. The idea is we have to isolate the variable, right? We got to get C by itself. And you say, what's happening to C? Well, you multiply it by 8 and then you add 4. Okay, let's unadd 4. AKA subtract 4. And I subtracted 4. I'm not trying to mess up. I do a pretty good job of it when I'm not trying. But okay, so now what do we do? Okay, so 1960 divided by 8. All right, so that goes into 19 twice, giving you 36, which is 4, giving you 32, which is 4. So what are we going to say? You can, what? Make 245 cubes with 1,964 toothpicks.
On the cube, if we don't put a sentence, would you get marks off?
Maybe. If it is a word problem, then it should be answered. So the question was, on the cube, if we don't put word, if it's a word problem, right, and it asks you like to figure out the area of something or that, then at the end you should give an answer which answers the problem, right? Say the area of the pool is 27.2 square meters or whatever, right? So, ideally you should put that in there. All right, any questions on picture patterns? No? Okay, so we're done.